All right, well, let's get started. I think there's still a few more people coming in, but that's okay. Um, Hello, welcome everyone. We're happy to have you here. This is our webinar series, New Energy, Conversations with Early Career Energy Researchers. So thank you all for joining us today. We're happy to have you here. So my name is Dr. Megan Litweiler. I am the Manager of Academic Initiatives at the Arthur L. Irving Institute for Energy and Society at Dartmouth College, and I'm excited to welcome you here today for our final talk of 2024, but we will be back again in January with more speakers. So if you're joining us for the first time for this webinar, I'll give you a little bit of background on our New Energy Initiative. So the goal of our New Energy program is to connect, empower, and raise the profile of early stage energy researchers and climate researchers. And one way that we do this is through the New Energy webinar. So we've hosted over 50 early career scholars so far who've been able to share their work with this broad multidisciplinary audience that we attract to this webinar. And then we also host an annual in-person New Energy Summer Summit that aims to increase the capacity of early stage energy researchers to accelerate just energy transitions through interdisciplinary scholarship and collaboration and exploration. And applications for our 2025 New Energy Summer Summit will be open in January. So if you are an early career researcher in energy and climate yourself, keep an eye out for that. And you can find info on the Irving Institute's website and also join our mailing list for updates on that. So we'll introduce today's speaker in just a moment, but first, just a quick note that after the talk today, we're going to have plenty of time for discussion. So please feel free to enter your questions using the Q&A icon at the bottom of your Zoom screen at any time during the program, and we will get to as many as we possibly can after the presentation. All right, so with all of that out of the way, I am delighted to kick us off today by introducing our moderator for this session. I'm going to welcome on Dr. Hunter Snyder. Hunter's an American scientist who studies the tools we use to make decisions in the home energy transition. He's a research scientist at the Thayer School of Engineering and a senior fellow at the Institute of Arctic Studies at Dartmouth College. So Hunter, I'm going to turn it over to you. Thanks so much for being here.
Thanks so much for having me. It's great to see Prabhat give this talk today. I'd like to just introduce you to Prabhat. Prabhat Hegde is a PhD candidate in operations research at Thayer School of Engineering at Dartmouth. And during his PhD, Prabhat has worked on multi-layer network theory to model interdependent infrastructure systems, designing rural school bus routes and schedules, and decision analyses in climate risk management problems. Prior to his academic foray, Prabhat worked at the intersection of the energy and transportation sectors, conducting industrial research on sustainable fuels and emissions reductions technologies. Prabhat holds a master's degree in energy and products from a French institution and a bachelor's of technology in mechanical engineering from Manipal Institute of Technology. In some low-lying coastal areas around the world, decision makers are beginning to consider managed retreat of human populations to adapt to sea level rise. One of the main challenges in designing a managed retreat strategy is determining when to trigger a retreat. Decision makers lack the basic tools and scientific understanding to evaluate whether the benefits of interim response strategies like beach nourishment outweigh the costs of waiting longer to trigger retreat. Prabhat will talk a little bit about this retreat project of his along with today's talk here. So I'll hand it over to Prabhat at this time. Thanks, Prabhat.
Thank you so much for that introduction, Hunter. And thank you so much for all of you for attending. And thanks to the Irving Institute upfront for giving me this platform to have this webinar. I'm just going to share my screen. Is everybody able to see my screen? I would appreciate a little thumbs up so that we don't have any technical glitches along the way.
It looks great, Prabhat.
Okay, perfect. Thank you so much. So with that, I'd like to start. So my presentation is titled, Should We Stay or Should We Leave? Multi-Objective Trade-Offs and Uncertainty for Coastal Planning. This is work done in collaboration with a research scientist in our group called Adam Pollack and my advisors, Vikrant Vazay and Klaus Keller. This project was also funded by the Megalopolitan Coastal Transformation Hub, which is an NSF project, which is a consortium of 13 universities, primarily in the Northeast, looking at coastal adaptation planning with real-world decision makers. So if you've seen the news in the last month or so, you would have noticed that there have been major hurricanes that have disrupted everyday life. But what is also interesting to notice, and a change in tone or discussion from what used to happen a few years ago, is that in popular media, there is the question of whether or not you want to continue staying in these risk-prone areas where you have hurricanes that come about pretty often. A few years ago, this was not even in popular discussion. There's a lot of resistance to it. It is a complicated problem as to what you do. And if you look at some academics that vision out possible things that you could do to counter that risk, you will see something like this. So there is someone that visions an image of the present and looks at what can you do to counteract that risk. And they present a slew of options, often used in combination of some sort. So they say you can either build a levee and protect the city. You could potentially elevate all of the infrastructure you have within the city. You could do a combination of the strategies that are mentioned here, or you could accept the risk and try living with it, or you can consolidate where you're not really having any livable housing along the coastline, but actually grow vertically and grow more inland, or you can have floating patches of cities that try to connect to each other. But how do we get there from here is a question that is very, very difficult to answer, both qualitatively and quantitatively. But it involves two key things to consider. The first thing is that this type of problem needs to consider multiple different competing objectives, things like economic growth, disaster reduction, social cohesion, and potentially looking at environmental effects of having such type of decision making. The second one is that the decision making is inherently composed of multiple options. So there are different levers to consider. So this is a very complicated example of what planning needs to look like in reality. However, what happens currently is things that happen in a town like this. So this is Rodant, North Carolina. To the top left, you see an image of the actual houses that are there in this coastal town along the beach, where you have elevated houses. And a few years ago, there were videos from this specific town that went viral because a few of the houses ended up collapsing into the sea because of erosion. So once a town encounters a problem like this, they actually start looking for solutions that are supposed to be taken at that point in time. So this town approached a consulting company, and the consulting company basically said, you could dump a bunch of sand and prevent the erosion and try to sustain your town for longer, but it's going to cost you something. You can choose to not intervene, in which case you will have more houses that go into the sea and potentially have environmental consequences because the septic tank is going to go into the sea and pollute the ocean and potentially affect both the economy and the ecosystem there. Or you could carry out a managed retreat program wherein you actually pay people to move out or move the entire houses or other housing stock inland and still kind of maintain that town cohesion. However, people are actually thinking about this from the perspective of making a decision right after a big hurricane or erosion that collapses houses. So the key question we are trying to address is if we take a longer time horizon, can we actually in some way determine when we nourish the beach, when we do nothing, and when we pay out people? And looking at some of the uncertainties involved in this problem and looking at multiple objectives. I just want to spend a couple of minutes talking about the complexity of managed retreat and why this foresight of when to retreat is important in terms of now. So if we look at the process of managed retreat, you'll see that it's a fairly complicated bureaucratic process. So FEMA has to allocate funds for this, and the funds need to end up going to the homeowner. And by the time this entire process happens, even post a disaster, it can take anywhere between 2 and 11 years for it to happen. So it's a long timeline. And preventively planning for the timing of retreat can potentially reduce this timeline and have cash flows in place for this to be enabled. And the second thing that I'd like to talk about is that there are many actors here, as you can see in this bureaucratic space. However, if we look at all of the possible managed retreats that have taken place so far from different federally funded projects across the world, and you map that on in this 4-quadrant axis, where you're looking at whether or not the move was initiated by the resident themselves and whether or not the managed retreat actually helped society or helped only the people that moved. What you will see is that in the most cases of managed retreat that have taken place so far, people have been evicted kind of forcefully, where they do not initiate the move, but there's a long process where they're consulted and some levers are put in place for them to move. At the end of the day, in most cases, it's a voluntary buyout, so the homeowner decides whether or not to move. But what we are trying to do is we're trying to look at this at a town level. We're not considering all of those individual complexities and saying that if there are bureaucratic mechanisms to work this out, there's an entire town that could move. So then the key question is, how do towns make such decisions? So when we go into that space, there are 3 key things that are currently problematic that we try to address. So in most of these decisions of how to protect coastal towns, retreat is not often considered as a possible management strategy. And then there are multiple competing objectives that are not taken into account at all when these plans are made. And there's a lot of uncertainty in the climate and economic parameters in a given town that are not considered in designing these strategies. So what we intend to do with our work is address these 3 research gaps. So in order to look at what exactly happens in the real world, we approximated and mapped out what the Army Corps does to make such decisions at a coastal town. So we present this in an XLRM framework where we say, hey, what are the uncertainties that are considered? What are the levers that you can use? And what is the metric of interest based on which the decision is made? So the Army Corps actually considers 3 possible values of sea level rise and 2 possible values of discount rate. And they fix something called a rotation length, which basically tells you how frequently should you nourish the beach. It could be something like once in 4 years or once in 5 years. And when they present the benefit cost ratios based on which the decision is made, they're basically looking at a single criteria to obtain federal funding, which is to pass the benefit cost ratio thresholds based on which the Congress makes the decision, which is a benefit cost ratio greater than 2.5. And then we said, okay, what have people done in the academic space to tackle this problem? And as a benchmark, we use a paper that was published by a PhD student at Dartmouth a few years ago, along with Professor Amelia Albert, where they added retreat to this decision problem and said, okay, we would like to maximize for net present value. However, we're going to consider more parameters that are uncertain. And for a combination of uncertainty, we're going to have a different sequence of actions every time. This works very well if we are completely sure of the climate parameters and the economic parameters that are considered. However, what we do to this problem is to actually consider decision-making under uncertainty by considering all those different possibilities. And we extend the objectives in this problem to actually capture the trade-offs between different objectives that a town might be interested in. So we actually try to maximize for benefits, minimize investment costs, minimize damage costs, and maximize something called reliability, which we're just defining as the amenity of having a beach. So you can naturally think of things like investment costs and damage costs actually having trade-offs, and that is exactly what we want to present to a decision maker. So the key idea here is that coastlines are actually fairly complex, and we actually map out how the system relationships that abstract this complex ecosystem look like from our baseline reference that we're using. So essentially, there are some socioeconomic parameters that are uncertain in the system. Things like how much does the aggregate property valuation of a town change based on risk perception for sea level rise? Or how much does the property valuation change based on the width of a beach or the discount rate, or dependent on how much the sand price is going to increase in the future? And then there are some geophysical parameters that impact the system. This is things like how much is the sea level rise going to raise? Is there going to be an impact on storm erosion based on the sea level rise increase? Factors like those. And these map on to state variables, things that you can actually see and observe, which in this case is the aggregate property valuation of the entire coastal town and the width of the beach. And you can also observe sea level through time. And all of these map on to metrics that a town might be interested in, which is basically things like net present value, damage costs, investment costs, and the reliability of having a beach or not. And into this complex system, at every point in time, you can influence it by choosing to retreat or to nourish. So this is kind of the setup of the system dynamics of this problem. Now we're going to look at what basically happens in an actual town in a stylistic fashion based on the expressions used in our baseline reference paper. So this figure, you see two parameters. One is the aggregate property valuation of the town in red and the beach width in blue. What you see is that the aggregate property valuation of the town goes down over time because of increased sea level rise. And there's a correlation between the erosion in the beach and the property valuation. Every time there is an erosion in the beach, the property valuation of the town slightly reduces. And every time we choose to nourish the beach, which is basically putting the beach back to its full width, we actually see a corresponding increase in property valuation. And at some point in time, there is a managed retreat that is carried out where the property valuation of the entire town goes to zero. And just as a cautionary note, this is an analysis done in a 100-year time horizon, starting from a baseline year, which is possibly today. So we're basically looking at sequence of actions that you can potentially have in a 100-year time horizon. So the key question then is, okay, if we have the Army core strategy and the net present value maximization strategy, how do you actually account for uncertainty, and what does that do to having reliable metrics to make decisions based on? So in this figure, what we show is these two strategies. One is the net present value maximization strategy and the stylized Army core strategy. And then we subject that to possible values of uncertainty in these different parameters and look at the expected values of costs and benefits here, just two objectives. What you will notice is that if I have just 10 combinations of uncertainty, depending on how I consider those 10 combinations, for the strategy about here, I could end up with a cost of somewhere around $2 billion or $4.5 billion. That is not a realistic metric or number for me to base my decision on. And as we keep considering more samples of uncertainty, we hit a stable value of metrics or numbers that you can actually make decisions on. And at around 10,000 combinations of uncertainty, we say that, okay, we're kind of sure of what the expected costs and benefits are for us to make decisions. So we need to consider relatively high sampling of uncertainty to actually be able to have reliable metrics. So then the question is, what does this mean for decision-making with multiple objectives? And I'll just briefly talk about that in the next slide. If there's one thing that you take away from today's webinar, I would like it to be this figure. And we're going to solely focus on the figure on the left before we talk about the figure on the right. And I'd like to draw your attention to what is happening here. So we map out where the Army Corps approximation without retreat lies in terms of benefits and costs. And we also map out the strategy recommended by net present value maximization relative to benefits and costs. And there are two individual points that are given to a decision maker. However, what is actually missing is that when we do a two objective optimization, we get a set of potential strategies with different retreat years, and there's a natural trade-off. You can choose to retreat very early, say in year 5, and have low benefits and low costs, or retreat later with higher benefits and higher costs. If you gave the decision maker an individual retreat year, they would not be able to see that point and base a decision. And a second point is if a decision maker is constrained by something, then these 2 points don't really cut it. Let's say a decision maker does not want the total cost to exceed 1 billion. In this case, they are going to be constrained and they should retreat somewhere around year 40 at the latest. And on top of this, there is the Army Corps benefit cost ratio threshold that is also mapped in this figure. So basically, if I say I know all the parameters very well and I'm going to consider their best case and I'm going to optimize, what ends up happening is that both the net present value maximizing strategy and the Army Corps strategy pass this benefit cost ratio threshold from the Army Corps. Now, let's look at the panel on the right, where we actually consider those 10,000 combinations of uncertainty and look at expected values of costs and benefits in this decision-making framework. So what you will notice first is that both the net present value maximizing strategy and the Army Corps strategy actually fail this threshold. And in addition, we have a smaller set of possible solutions with a retreat year ranging from year 10 to somewhere around 50 that are actually likely to satisfy the Army Corps benefit cost ratio threshold. And the other thing that I want to briefly mention is that because we've considered a high combination of uncertainties, when we do the optimization every single time, we end up coming up with the same Pareto frontier with the expected reliable metrics, which really helps the decision makers have reliable metrics to base their decisions off. So this is just a two objective example. We actually have 5 objectives in our problem. And in the next slide, I will basically talk you through how decision makers can narrow down these sets of strategies based on their preferences in a 5 objective set. So this slide is a little complicated to digest, so I'm going to dissect it slowly. So I'd like to draw your attention initially only to panel A in this figure, where we run a 5 objective optimization to look at trade-offs between the different objectives where a decision maker is interested in. So what you'll notice in the top panel is that there are many lines crowding up the space. Each line there represents a sequence of actions that you can take, which is basically when you do nothing, when you nourish, when you retreat. And all the lines that are colored basically have a retreat year corresponding to the color in the color bar. And if you do not have the possibility of retreating in your sequence of actions that you could take, then it's colored in blue. So the top panel presents the decision maker with the entire sets of possibilities. And there's some intuitive things that you will notice straight away. Say, for example, that there are trade-offs between investment costs and damage costs. You can have low investment costs, but potentially risk very high damage costs. Or you can invest in protection quite a bit right now and have low damage costs in the future. In panel B, we filter out only the strategies that do not have retreat as a possibility. And what you will notice is that these strategies have a wide possibility of net present values, not quite the maximum, but you can hit it. And we present a decision maker that is interested in potentially delaying retreat or not wanting to retreat, what the metrics would be under uncertainty in panel B. In panel C, we actually look at the realism of getting federal funding, which is looking at strategies that have a benefit cost ratio greater than 2.5. And what we notice is a smaller band of possible retreat years, ranging from somewhere between 40 and 51 or 52. And then we say, okay, in the next 100 years, we would like to have a beach at least for 90 years for things like tourism and continuing accruing those amenities or benefiting the local economy. And in panel E, we actually filter for both criteria. We want to have the beach and we want to have the Army Corps threshold satisfied. And then we're left with just a single strategy with one retreat year, which in this case also maximizes for net present value when you consider the benefit cost ratio threshold. So this is how a decision maker can actually filter out and design strategies based on their preference with a type of framework like what we're presenting. However, if you choose different strategies, the uncertainty also impacts the strategies differently. And this is what we would like to show in a panel like this. We perform something called a multivariate sensitivity analysis. And in this panel, I'm showing you two different strategies. One on the top panel is the strategy that is approximated from the Army Corps actions. And below is the strategy that a decision maker could filter out. That is a feasible strategy that also maximizes for net present value. And we compare how uncertainty in these different parameters impacts these two strategies differently for different objectives. So if we just look at panels A and C, where we compare how the net present value for these two strategies is impacted by uncertainty, what we will see in these type of spider plots is two things. So if there's a solid circle in the center of a parameter, that is indicating how strongly that parameter standalone impacts the objective. If there are lines between two parameters, that looks at how the correlation between two parameters impacts the objective. And the hollow circle outside shows the total influence of a given parameter on that objective. And here, like you can clearly see that the Army Corps strategy is more susceptible to sea level rise and increase in baseline property valuation over time. And their connected effects actually influences net present valuation a lot more than when you choose to retreat slightly earlier. So a decision maker can potentially be made aware of the types of uncertainties that are going to influence their decision across the time horizon. And the other key question that you can think about is, so far we've been talking about doing in our analysis for a 100-year time horizon. So what actually happens if you just look at 20 years or 25 years? And that is something that we're going to briefly address in the next couple of minutes. So I would like to draw your attention only to the panel on the left at first. In this panel, what we're showing is if a decision maker says, I'm interested in maximizing for net present value, that also passes the benefit cost ratio test, when should I retreat? Right? That is the key question that we're trying to answer. And if you do not consider any uncertainty at all, we're gonna just stick to the baseline reference retreat year from Cutler et al. In this case, which tells us, okay, for the best guess parameters, retreat in year 72. And then we start looking at, okay, we just consider 10 combinations of uncertainty, and that is giving us a different retreat year for our strategy of interest, which is not very useful in designing a policy. But as we start to sample more combinations of uncertainty, especially 10 to the power of 4 or 10,000 uncertainties as we consider, we're able to reach a stable guidance or guideline on the retreat here, which is basically says retreat in year 52, which is slightly different from when you optimize considering that you know all the parameters well beforehand. And the other thing that we consider is if we carry out the analysis for 25 years or 50 years or 80 to 85 years, does that recommendation of the retreat year stay the same? And here we can see that if we do the analysis for a shorter time horizon, we end up getting a recommendation of retreating early. The Army Corps actually solves these type of problems in a 50-year time horizon, and their recommendation would then be to not retreat. However, if you look at a 50-year time horizon at a given location and say not retreat, and you slightly increase that time horizon, it is telling you to retreat sometime in year 52 or 51. So basically, you're not able to proactively plan for retreating right after the end of the time horizon. So in other words, what we're saying is if you do not consider enough samples of uncertainty or a long enough time horizon, you could be in this yellow region where you keep getting different retreat years based on how you sample your uncertainties and what time horizon you consider. However, if you sample enough uncertainties and have a long enough time horizon, you're relatively safe in deciding on the strategies that you plan for. With that, I'd like to recap the 3 key findings from the study and things that we add on. So considering retreat is crucial to finding satisficing coastal risk management strategies. By that, I mean being able to keep the decision makers' preferences in mind and propose strategies accordingly. Considering multiple objectives is actually something that enables decision makers to pick from a set of strategies as opposed to giving them one strategy that's a little myopic to the planning problem. And the last one is better representation of known unknowns or uncertainties actually changes the expectations and drives earlier coastal retreat. With that, I'd like to thank you for your time and thank you for coming to my talk. And I'm happy to address any questions. Thank you.
Prabhat, thank you. That was wonderful. Let's see if we have anyone in the chat who's posted any questions. I don't see any yet. I had a question for you, Prabhat. It's more high level and more applied in a way. I had asked about your experience engaging with decision makers in the real world and or members of the Keller Lab engaging with decision makers in the real world. And I'm wondering if you have any sense of what helps them understand even this idea of many objective optimization or multiple objective optimization. And in particular, I'm thinking about this Pareto frontier because it's a really important decision support tool in and of itself, but it's maybe not so apparent to some folks as to what's depicted on that front. Do you have anything that you want to share with us about?
Yeah, so I think it does call for a lot of stakeholder engagement and training to be able to translate this into real actionable insights. However, there have been successful models, say with Del Torres in the Netherlands, where they actually make decisions by looking at decision support tools that involve multiple objectives, or certain water utilities in Rio Grande Valley or the Colorado Basin. And I'd also like to point out that there's a recent mandate even to the Army Corps that used to look at net economic benefits or cost-benefit ratios exclusively in making decisions. However, they have new guidelines now in something called ESS. I think it's called environmental, societal, and social, or something to that effect, which basically says you're supposed to look at multiple things while implementing a project on the ground. However, there are no guidelines on how to make these decisions. So the Army Corps right now is going back to its drawing board and basically saying, how do we weight these objectives? It's definitely something that is coming to prominence in the policy application fold quite a bit.
Thanks, Prabhat. Does anyone else have questions for Prabhat? I have many, but I don't want to take over, so to speak. We had talked earlier about the possible applications of this type of work in other areas. And if I remember correctly, you have some comments on this and maybe something else you could share visually. Do you want to share a little bit of that, Prabhat?
Yeah, so I have a few additional slides if people are interested about how this type of work could segue or be useful in other possible research application areas. And a lot of it has to do with the spatial resolution of the problem that we're talking about. So I'm just possibly going to put in a couple of ideas here, and I would welcome any sort of engagement or interaction or thought process based on what I'm about to say. So one thing is, we're really in this world where we have to make global decisions along a coastline. And I looked at what the state of the art is in making such recommendations at a global level. So there is this reference that I've put below called the SEAM model that basically uses a global coastline data set that segments the global coastline into 13,000 segments, where they basically look at what should each segment do for a single objective optimization for that segment. We're not doing a global optimization, but what is the best decision for that segment? And what they consider is 4 different levels of protection, where they just look at increasing the height of a seawall, or 4 different levels of uh, retreating, where they retreat to protect against a 10-year flood or 100-year flood or 1,000-year flood. Uh, and the current state of the art there actually does not consider other possibilities apart from a seawall. And there is no decision-making collaboration between segments. And coastal communities are tied to a strategy that they pick. So if I pick to protect to a 10-year flood, I have to only consider protecting to a 10-year flood for the next 150 years. But in reality, once you have a level of protection, you might want to have a higher level of protection in the next time period. And it's not really like an adaptive decision-making framework. And something like my multi-objective framework can actually add a lot more insights to say, looking at potential retreat years along a coastline. Like, we're not talking about retreat years here. We're just talking about protecting to a certain intensity of flooding. So that could be very helpful in deciding on, global policies of having people or not along coastlines. I'm going to pause there for a second.
Yeah, I was just noticing a question coming in. Someone writes, how do things like insurance markets play into managed retreat? As in, it becomes crazy expensive to insure coastal houses, but retreat hasn't happened. Are those variables considered?
So that's a very good question. That is not something that we've explicitly considered in our system relationships. That is also because of the resolution at which we're considering our problem. I think when you disaggregate this decision-making to the decision-making of an individual house, 100% insurance markets play a big role. Whether or not someone insures your house impacts whether or not you accept a buyout. And there are a lot more complications when you want to actually couple the decision making at an individual homeowner level to the decision making at a town level. We circumvent dealing with some of these things because we're aggregating it at the town level, but 100% there is a research need to disaggregate that decision and include insurance markets for individual houses in that consideration. Yeah, that is something that could evolve from the framework we have. And ideally, it's a 2-stage problem that happens in reality, that a centralized planner makes a decision. A town says, okay, we're going to retreat 50 years from now. Based on that, the individual constituents make their own decision whether or not they'll stay, because there's some risk perception. And based on their decision, in the next deliberation, the town changes its decision. And it's actually this interplay between what individual homeowners decide and what the town decides that actually drives some of those dynamics. And that's something that we would like to capture eventually.
And those feedbacks, I'm assuming, are not presently part of the model. That is between those lower level units and the municipal
No.
or
No, that is not something that is currently included, but it's something that I think would be great to include in frameworks like this.
Yeah, I was thinking personally about the mention you made about sand prices, which seems so banal, but I'm guessing that it's difficult to calibrate your model to account for volatilities in raw materials like that. Is there any, I mean, there must be other factors like that that are difficult to improve.
Yeah, 100%. And you know, the thing is we use some like stylistic relationships to represent things like sand prices, like, you know, potential exponential increase in the price of sand, for example, and a coefficient for that. However, what I want to point out is that if tomorrow someone comes in and has a sophisticated sand supply chain model, for example, where they're looking at the source of sand, where like your beach is located, how many trucks it takes, and how much fuel is burnt along the way. So there's like actual counting for that project. If you have a more finely resolved cost model to represent this in a system relationship, you could potentially just plug it in to my multi-objective framework, and it will reflect that improved resolution in the supply chain or costing model and impact results accordingly. That's always something that you could bring through. And there are many other things, like we're obviously stylizing how coastal erosion happens with a physical expression, but tomorrow you observe something else and you want to include that in the framework, it is possible. The key thing with this multi-objective framework is it's tying in these pieces together from geophysical modeling, from economic modeling, from modeling individual equations, and looking at multiple objectives under uncertainty. So
Is there, do you have anything that you want to say just about the general approach of combining all of these different pieces together? That I'm thinking mostly about the programming languages and the various integrations so that there is some forward compatibility for, say, bringing in some sand model or something like that into the future. What is the approach that other scholars who are doing this work in multiple objective optimization are taking when it comes to programming or building out the models themselves so that they're reproducible or updatable, so to speak?
So there's a fair bit of work in three domains that I can think of. The first one is primarily algorithmic. Multi-objective optimization problems are not very easy to solve to optimality. And there's some like innovation going on with, you know, making genetic algorithms that solve these type of multi-objective optimization problems faster and customize them to the set problem. That's one research focus. The second one's actually, hey, how do you build tools that embody whatever research is going on in these algorithms and make people use them in an effective manner? So I see historically a lot of this has happened in programming languages, primarily in Java and Python. And I see that going to continue. Potentially, you're going to have a few more packages in Julia. And most of the times, you know, there's like an interplay between the languages, and it's like often easy to write things out or read in things from one language and implement something else in the other. So I think it's not that rigid to feed in or to interplay with this model. Say if someone develops a sand model in some other programming language, you could easily output that in one way and feed into this model in a different way.
Nice, nice. I see another question here, and maybe we can take one or two more before we wrap up. Someone here writes, if when the federal government moves to being smaller and the funds for buyouts reduce or disappear, what kind of approach could help individual towns and citizens make decisions on the local level?
So that's a very good question. And it's something that is anticipated. I think as we have more and more events, the federal government's not going to have money to buy out all properties. So at some level, they're also thinking, how do we induce private modes of retreat so that people retreat on their own in a timely fashion, as opposed to us having to pay pre-hazard market value all the time? And some levers from a federal perspective have been to say things like, okay, if you have a disaster for the first time, we're going to pay you some money to still stay in place by elevating your house, for example, to counter that hazard. But a second time your house is damaged, we did not do anything. It's entirely on you. So at the first level, they actually give the homeowner the choice whether they want to stay in place and, accept some kind of support for elevating their house, or whether they would like to take a buyout. And if they fail to take a buyout, then they're on their own. So they enforce policies like this, and being aware of policies or mandates in this space in general would be slightly important. And if you're an informed homeowner, I think you would have to go one step ahead. Say, for example, what I noticed when we had the recent hurricane hit Asheville in particular, many people with mortgages did not have flood insurance on their house because they thought they were considerably inland, and they're suffering from like adverse consequences of not having any flood insurance on their house at all. So that's also something to keep in mind. So stay abreast of policy measures at the federal level, and also look out for signs from the flood insurance market at a local level while making your own decisions, is what I would say to constituents.
Thanks, Prabhat. Do we have any other questions? Okay. Prabhat, it's really exciting to hear about this work and how it has so much use in so many other really important, complicated, uncertain problems. Thanks for sharing it with us today. And thank you all for joining us. And we look forward to seeing you in the next series we have.
Yeah, thank you so much.
Yeah, pass it
Yeah,
off to Megan here for closing remarks.
Thank you. Yeah, thanks, Hunter, and thank you, Prabhat, for a great talk. It was really fantastic to have you and hear about your work. And we're looking forward to hearing more about how your research goes as you move on in your career. So please keep in touch and keep us posted. So this is our last talk of 2024. So we'll be back after the new year with more talks in January, February, and March. We have folks who are going to be talking about operations research and environmental justice and environmental economics. So really excited for what's coming up. But I really want to thank Prabhat again for sharing this really important work with us, and Hunter for moderating a really great discussion. So thank you for being here, and we look forward to seeing you again.
Thank you so much.
Thanks.